Alright, we're going to work through problem 38 in chapter 10. The problem says that you observe a 2 kilogram particle moving at a constant speed of 3.5 meters per second in a clockwise direction around a circle. So that's going to look like this. Let's draw a circle. This is describing the path. It has a radius of 4 meters. Around a circle of a radius of 4.0 meters. And it is a constant speed. So here's our particle. It has a mass of 2 kilograms and has a constant speed of 3.5 meters per second. Well, already we get a, what does that mean? What's constant speed? So it says constant speed of 3.5 meters per second. Well, it's not angular speed or angular velocity, it's angular speed, and it's in units of meters per second. So that must be a tangential speed. It's moving clockwise, so that means we're going to draw a tangent line right there, and that's going to describe the velocity, or the speed, right? This is the constant speed of 3.5 meters per second. The question then asks, what is its angular momentum, including direction about the center of the circle? And so, we have this particle here, and we want to know its angular momentum. The angular momentum is equal to r, the vector product of r and p, where r is simply the displacement from the point of interest. So here we have, it wants to know about the center of the circle, what is the angular momentum, including direction about the center of the circle. Well, it's here's r. Okay, and it has a magnitude of 4 meters and a direction that depends on where the location of this mass actually is. So its momentum is equal to its mass times its speed. So the magnitude of its momentum is equal to its mass times its speed, or the magnitude of the velocity. So we can figure out what that is. We know what its mass is and we know what its speed is. And so we want to know its direction. Well, we can figure that out, right? We know that this is equal to the magnitude of r times the magnitude of p times the sine of the angle between them. But that doesn't tell us, that tells us the magnitude of the angular momentum. And we can figure that out. The magnitude of r is 4 meters. The magnitude of the momentum is its mass, which is 2 kilograms, times its times its velocity, which is 3.5, the magnitude of its velocity, which is 3.5 meters per second, times the sine of the angle between them. Well, the angle between these two, if this is moving at constant speed, the direction of this is simply going to be tangent to the radial component. So this angle between the two is going to be 90 degrees. So if this is equal to 90 degrees, or pi over 2, that means sine of pi over 2 is going to be equal to 1. And so we simply calculate this value, which is, what is that? It's 4. Let's do 2 times 3.5 is 7, times 4 is 28. So that'll be 28 kilograms meters squared per second. Right? That's the magnitude of our angular velocity. Then we need to talk about the direction of our angular this is the magnitude of our angular momentum, and then asked about the direction. And the direction, regardless of where this object is, we can do our right-hand rule. We take r, cross into the momentum, so r cross p, and that tells us that the angular momentum is into the page. And that doesn't really matter where we do it, right? We could do that at any point. We could have made a sketch where the object was over here, so that r would then be in this direction, coming down, curling into the direction of the momentum, and again into the page. So the direction of L, this is L, the angular momentum is equal to 28 kilograms meters squared per second, and into the page. Alright. It then goes on to ask about what is its moment of inertia about an axis through the center of the circle and perpendicular to the plane of motion, right? So we can figure that out. We've probably done this a million times, where we've talked about here's a ball. What is its moment of inertia of a single object like this? It's really simple to figure out the moment of inertia. we simply take its mass, the sum of the masses times the radius squared. So there's only one mass, it's located at a distance of r, so it's simply m times r squared, right? That's all the moment of inertia is. And the last one is, what is the angular velocity of the particle? Well, we can figure that out, right? We know what the angular momentum is, we know what the moment of inertia is. We can actually calculate a value for this. This is very easy to do. 2 kilograms times 4 meters squared. That's 4 squared is 16, times 2 is 32 kilogram meters squared. And the last part of the question says, what's the angular velocity? What's omega? So the angular velocity, we know that the moment of inertia times the angular velocity is equal to the angular momentum, and even if we want to include the direction, that's great. So this, we can plug in the numbers that we have solved for previously. So the angular velocity is equal to 28 kilogram meters squared per second divided by 32 kilogram meters squared. And what happens to our units? Our kilograms cancel, meters squared cancels, and we get 1 over seconds, which is what we would expect, right? That radians, remember, is a unitless quantity. So this angular velocity, the magnitude of this angular velocity is, we can even talk about the direction, right? This was 28 kilograms meters squared per second into the page, and our angular velocity is in the same direction. So this is going to be equal to something pretty close to 1, actually, something a little bit less. So let's say that it's, I'm not exactly sure, we can figure that out, something like 0.9, I don't know, 92, let's say 0.92 radians per second, and that is into the page, right? Slick. That was problem chapter 9, 38.